Hello, I'm Mario Motta. I'm a researcher at IBM, and today I'll be giving you a seminar on the topic of Hamiltonian simulation. I'll be giving an overview of the research landscape and of some recent capabilities. This talk is shared with my colleague Kevin Sung, who is going to give an hands-on tutorial. And the goal of my talk is to set the stage for this tutorial and also maybe offer some context and an invitation to attend other tutorials and talks in the QDC. And so let's start by bringing up the IBM roadmap, which was also featured in the main talks earlier today. As we have seen, our simulation capabilities have improved over the years, and that's certainly in part because we have larger devices than it was possible before and lower error rates. And the perspectives for the futures, which were articulated by Matthias Steffen in this morning's talk, are also very encouraging for the future. That we have been able to do more interesting, more challenging simulations than before is also the result of another effort. Not only our devices advancing capabilities, allowing us to do more, but there is a continued effort in inventing, optimizing, refining algorithms which may bring down the resources needed to solve a certain problem with some level of accuracy and make them more feasible, closer to the capabilities of today's devices. This sort of pattern has been unfolding in various application domains, which are listed in this chart. I'll be telling you only something about the first one, which is on the left, Hamiltonian simulation. Hamiltonian simulation in itself is a very broad field, and today we'll be touching briefly upon two subfields. One, the simulation of Hamiltonian eigenstates, the solutions of a time-independent Schrödinger equation, and the other, the solution of Hamiltonian dynamics, of the time-dependent Schrödinger equation. For each of these sub-problems, I'll try to articulate some reasons for which this is an interesting thing to look at, give some indication of what quantum computers can do in this space, both in regards to current capabilities and possibilities for the immediate future. And I'll try to do so by highlighting the research of our partners, which is also, in part, the content of the other talks of the event. Let's start from the simulation of Hamiltonian eigenstates. And let's start looking into one concrete example from the Cleveland Clinic. So in this particular case, they have considered the study of binding energies. The question they ask themselves is, I have two molecules, I want to determine if they bind, if they are more stable together than far apart, and how strongly do they bind. And for that purpose, they have taken the two molecules, and as a function of the distance separating the two heavy atoms, oxygens on the left for the water dimer and carbons on the right for the methane dimer, they computed the ground state energy as a function of the distance by solving a time-independent Schrödinger equation. And out of it they computed the binding energy. This is a very subtle study because the mechanism that drives the binding is not the normal breaking or formation of covalent bond associated with a large energy scale. It's a non-covalent interaction, dipole-dipole between the two water molecules and van der Waals between the two methane molecules. I invite you to take a look at the energy scale, which is quite fine. 5 kcal per mole in the water dimer, sub kcal per mole in the methane. It's certainly a good thing that we have gained the ability to do some calculations of this kind. The future is adding more realism to these kinds of calculations and also starting to look at the competition between different non-covalent interactions. Another example, still from the Cleveland Clinic, is looking at conformational energy differences. In this case, you have a molecule called cyclohexane, which has a given brute formula, CH2,6, but can be found in different geometries. One is the chair, the other one's the boat. It's quite important for us to know these geometries and also to be able to accurately compute the difference between their ground state energies. And that's what the Cleveland Clinic has been doing. It's important to find out the most stable geometry and also the energy differences between the various geometries. As you can see on the right, their simulations, light green to dark green, go from cheap and low accuracy to more expensive but also higher accuracy, and in that regime the energies are predicted both in the correct order but also with quantitatively accurate energy differences. More of these topics will be in the talk by Daniil Kaliakin and Tadeusz Pellegrini, which I invite you, if you are interested, to attend. Another partner, Boeing, has been looking at how chemical reactions unfold. Information about reaction dynamics come from reaction energetics, and in particular what they have been doing is computing the ground state energy as a function of nuclear coordinates as the reaction unfolds. Here you see a nitrogen abstraction by a CH3 radical. The radical lands over a larger organic molecule, steals a nitrogen atom, and then flies away as a CH4, leaving behind a radical. These computations they have done for active spaces of different size, comparing with classical methods, and they have focused on the activation energy, the difference between the energy of the transition state and the reactants, what is needed to trigger the reaction, which is around 16-17 kcal per mole, and then also the reaction energy, the difference between energy of reactants and products, which is very close to zero. This is a reaction that doesn't release or absorb too much energy at all. I have been mentioning essentially ground state studies in quantum chemistry, but Hamiltonian eigenstates have a whole world of applications outside of it. I just quote you one small example briefly from Rensselaer Polytechnic Institute, which is looking at ground state correlation functions. So we are now in condensed matter, and we are not just looking at energetics but at properties, with the goal essentially of elucidating the nature of the magnetic correlations in a spin model, and also observing how magnetic correlations onset and transform as some parameter in the model is changed. In this case, the competition between a nearest neighbor and a second nearest neighbor interaction strength. Behind some of these calculations, there is an algorithm called SQD, and which is the subject of Kevin Sung's tutorial, and it is essentially an example of how useful it is to test, change, introduce, refine, and study numerically algorithmic performance to make progress in the simulation domain. So the first algorithm to be systematically used on quantum devices was variational quantum eigensolver, introduced in 2014. Since then, we had a steady increase in the computations that we could do with this method, and at every step we learned a great deal, both about the devices and about the structure of the algorithm itself. the introduction of SQD has essentially expanded greatly our simulation capabilities. And Kevin will be going more into the details of it, and I'll just give you a brief overview as an introduction to his tutorial. So the SQD sample-based quantum diagonalization method is a method that imposes a certain approximation onto the solutions of the time-independent Schrödinger equation. This approximation is an approximation of sparsity. Although we are trying to solve an eigenvalue equation in a combinatorially large Hilbert space, meaning we technically have to deal with combinatorially large matrices and vectors, the assumption behind SQD is that the combinatorially long vector we are looking for has a subset of entries, certain rows, with larger coefficients than the rest. Let us make a thought experiment. Let us say that we know which entries they are, and that all the other entries are negligible for the purpose of a certain calculation. Then what we can do is to project the combinatorially large Schrödinger equation into a much smaller subspace, spanned only by the relevant entries of the vector in the sense mentioned above, and we are basically left with the diagonalization of a much smaller matrix. In the current formulation of SQD, but there could be more general formulations, these entries correspond to electronic configurations, and by this term I mean Slater determinants, which are depicted in the bottom right part of the chart. All of this is fantastic, but you could tell me, who tells me where are the dominant entries? And there are many strategies to figure out where the dominant entries of the vector are. Classical methods of selected configuration interaction type rely on an iterative search. We start from a very short vector with a small set of non-zero entries. We can then progressively expand the set of configurations through the application of the Hamiltonian, and then rank them, rank the entries of the expanded vector by importance, trim the ones that are less relevant. So after this pruning, continue. It's a sequence of expansions and prunings, expansions and prunings. There are indeed many situations in which this procedure is fairly efficient at approximating Hamiltonian eigenstates. SQD is one of the algorithms that adopt a different procedure. The idea is to produce a quantum circuit, one or more quantum circuits, and to draw samples from these circuits, samples which correspond to Slater determinants in this particular formulation. So essentially we have a stochastic alternative to the well-established deterministic procedure. Kevin is going to tell you a bit more about SQD in his tutorial, which also going to have a hands-on component, very useful in my perception. But what I should wish to point out is that it may be worth to encourage a critical approach to this method. In other words, please, when you attend the tutorial, when you think about it, don't consider it a settled algorithm, but something that is undergoing change. It's being understood, it's being generalized, it's been made more efficient. I'll just give you one indication of how much these methods can be improved from the research of another partner, Riken, in Kobe, Japan. So Riken, in collaboration with IBM, has been looking at ground state simulations for iron sulfur clusters. These are very important biological motifs. However, they were chosen because they feature very intense electronic interaction due to partially filled D shells in the iron atoms. What you can see in the figure on the left is a stack of results from the original SQD paper and a follow-up paper. So on the left, the top line is R3-FOC, restricted closed shell R3-FOC, a method that for this kind of system is very inadequate because mean field fundamentally breaks down, especially in this flavor, in the presence of strong electronic correlation. In fact, it is around 326.5 R3, whereas the MRG, a very accurate classical method, is down at 327.25. This is a very substantial difference. And it's in R3, and kcal per mole, the kind of unit you have seen in previous charts, is around a milli-R3. So there's a very substantial gap between R3-FOC and the MRG. There's a line called 2024 state-of-the-art quantum. That's the SQD calculations in the first paper. And to give you an idea, they are, of course, lower than R3-FOC. They capture some electronic correlation, but they're higher in energy than CISD, configuration interaction singles doubles, and an unconverged CCSD, coupled cluster singles doubles. Two methods that for strong correlation are indeed not very successful, and they're very much above the MRG as a matter of fact. Now, thanks to a combination of improvements in both the implementation, more efficient routines for diagonalization, access to quantum devices with lower error rates, but also of the algorithm itself, the ability to change parameters in the circuit and the ability to progressively retain configurations as the sampling unfolds if these configurations are deemed useful for ground state approximation, we have been able to push our SQD energy from the magenta line, 2024 state-of-the-art, down to the blue, orange, and green points, which are still very much above the MRG. However, upon carrying out an energy variance extrapolation, which is a well-understood procedure in precision many-body physics, we also gain a few more hundreds of milli-Hartree, and now our extrapolated quantum energy is a little bit lower than 327.1. So from the first calculation to the second, there has been substantial changes. And so the invitation is to consider SQD, but also other quantum algorithms, as something alive, something where everybody can look critically, examine, find limitations, and propose refinements. I will not cover algorithms beyond SQD in my contribution. However, if you want to know some recent theoretical developments in this line of investigation, I invite you to attend the talk by Kunal Sharma and Javier Robledo Moreno later in the conference. I've only mentioned ground state properties, but the time-independent Schrödinger equation has many solutions indeed, some of which, one of which is the ground state, the other are excited states. And the study of excited states with this sort of algorithm is very much in its infancy, and excited states tend to have a more lively electronic structure than the ground state in some situations, and so they are certainly very compelling candidates for interesting computational studies. And so for some future developments and areas, an invitation to attend Kunal and Javier's talk, and also to consider excited states. So with this, the time comes to leave you to Kevin's hands-on section on the sample-based quantum diagonalization algorithm. Kevin, the floor is yours.
Hi everyone, I'm Kevin Sung. I'm a software developer at IBM, and right now I'll just be giving a quick tutorial on our open source implementation of SQD. So on this slide here, I'm just showing you a diagram of how SQD would fit in a workflow. So in the picture in the middle, you can see that there's a quantum processor on the left side, a quantum system that has a quantum processor, and in SQD we're using this quantum processor to sample electronic configurations from the quantum processor, and then it gets passed to the classical computer, which is here on the right side, and the diagonalization is performed on the classical computer. So we've implemented the SQD algorithm as a Qiskit add-on. Now, Qiskit add-ons are open source extensions to Qiskit, implementing various research tools, which we hope you'll find useful. And I'm also showing here the link to the research papers on SQD, as well as the GitHub repository, where you can find the source code for our implementation. Okay, so now to go to the tutorial, first I'll actually show you how to get to the tutorial. You'll go to the IBM Quantum Platform website, quantum.cloud.ibm.com, and you go to the tutorials here. The SQD tutorial is actually under sample-based, is under this section called verifiable sampling algorithms. And yeah, so this is the tutorial, and I'm not going to go over it in too much detail. I'll just point out some key parts that might be helpful for you to understand the tutorial when you go through it yourself. So the tutorial begins with some chemistry background, and I guess an important part is this here, the expression for the molecular Hamiltonian, or maybe make it a little bigger. Now this is, in chemistry, this is what the molecular Hamiltonian looks like in second quantization. And here the A and A daggers are the fermionic creation and annihilation operators, which satisfy these anti-commutation relations. And in essence, you can just think of these as big matrices, and the Hamiltonian is actually specified by the coefficients of these matrices. And there are going to be two arrays of coefficients. You have the HPR, which we call the one-body tensor, and the HPRQS, which is the two-body tensor. These are just arrays of coefficients, or they're also called molecular integrals. And in this tutorial, we use a quantum chemistry package called PySEF to generate these integrals. But of course, you can also bring your own molecular integrals from your existing quantum chemistry workflows. And the particular ansatz that we use in this tutorial is the LUCJ ansatz. And this is, it shows the expression for the quantum circuit for the LUCJ ansatz. And a key fact about the LUCJ ansatz is that it can be implemented efficiently on hardware with limited qubit connectivity. So here's a picture showing how we might map the qubits for an LUCJ ansatz onto a square lattice. So normally we would map the spin up orbitals to a line and the spin down orbitals to a line, and we'll put these lines in parallel. And for the LUCJ ansatz, the reason that it can be implemented without any swap gates is that we only keep certain interactions that can be implemented directly on the hardware. So for within the same spin sector, we'll implement interactions that are between neighboring qubits on a line, whereas between different spins, we'll only keep the interactions within the same spatial orbital. So here, for example, we have an interaction between the spin up index 0 and the spin down index 0. And same with 1 and 1. But we won't have, for example, these cross interactions. And so the interactions that are allowed are going to be specified by these index sets, right? So the J alpha alpha here represents the same spin. So this set of index pp plus 1 indicates interactions that are nearest neighbor on a line. And then here, for the J alpha beta, indicates interactions for opposite spin. So here we have the same index for both spins. And the actual connectivity on our Heron devices right now is actually heavy hex. So that's a different connectivity from the example I just gave. And here's an example of how we would map the LUCJ onto a heavy hex. So again, we still have these parallel lines for the different spin sectors, but now we include additional ancilla qubits to mediate interactions between the different spins. And we also only keep every 4 opposite spin interactions rather than every 1. And so that's, here you can see the index sets that would describe this kind of mapping. Okay, and here you're just giving you an overview of the SQD workflow again. Okay, so at the beginning of the tutorial, we are using PySCF to generate the molecular integrals. This is just basically some boilerplate code. And again, if you have already your own molecular integrals, then you can just load them here. And so here, H core is going to contain the one-body integrals, and ERI is going to contain the two-body integrals. And here we're going to run CCSD, or coupled cluster singles and doubles, which is a classical quantum chemistry method that's quite commonly used. And here, the reason we're running CCSD is because we're going to use the outputs of CCSD to initialize our LUCJ ansatz. That's another nice feature of the LUCJ ansatz, is that because it's physically motivated, it can actually be initialized from the output of a classical computation like CCSD. And here, this is going through the initialization of the ansatz, which uses the FFSim package. So FFSim is another open source package. It's actually a state vector simulator for quantum chemistry circuits, but here we're using it for its LUCJ ansatz functionality. So here we're saying that we're only going to have one repetition of the ansatz, and then here we're specifying the indices giving the allowed interactions in the LUCJ ansatz. And so this is the syntax for creating an LUCJ ansatz object from the T amplitudes that we got from CCSD. And once we have that LUCJ ansatz object, then we can create the actual quantum circuit. So in this circuit, we're first preparing the Hartree-Fock state, and then we're appending a gate to represent the LUCJ ansatz, and then finally we're going to measure the qubits. Once we have the circuit, we're going to actually transpile it to a specific hardware backend. So remember, actual quantum processors will only have a limited set of gates that can be directly executed. So when we have a high-level circuit, for like the LUCJ ansatz, we have to transpile it down to the instruction set architecture that the quantum processor actually understands. Okay, so this is the syntax for performing the transpilation. So you'll note here that there's actually a hidden block of code that we're using to get the zigzag physical layout. So the zigzag refers to this picture up here for the LUCJ mapping for the heavy hex connectivity. So it's going to actually try to find the best zigzag pattern on the processor that we chose based on the calibration data that's reported. And one thing that to keep in mind when you're constructing LUCJ circuits is that when you perform the transpilation, you're going to want to set the pre-init stage of your pass manager to the ffsim.qiskit.preinit stage. And what this does is it adds additional steps to your transpilation to specifically optimize fermionic quantum circuits. For example, it will merge adjacent orbital rotations, and also if it sees an orbital rotation applied to a computational basis state, which happens in this ansatz, for example, because we're creating the Hartree-Fock state, and then the LUCJ circuit begins with an orbital rotation. It'll actually optimize that to a more to a gate sequence that uses fewer gates. And this is just showing an example that it actually makes a difference. If we don't add the pre-init pass, then our circuit ends up with nearly 4,000 2-qubit gates, whereas if we include it, then there's fewer than 2,000. And so finally, once we've transpiled the circuit, we can actually run it on the QPU, and here we're going to be using the sampler primitive because we're going to be sampling bit strings from the QPU. And once we have the actual results from the quantum hardware, we can perform the diagonalization. Now, the entry point to the diagonalization function is this function called diagonalize fermionic Hamiltonian, and this function will take in the bit strings. Here, that's the pub result .data.mes variable here. It takes in the bit strings that were sampled from the QPU, as well as the description of the Hamiltonian here, again, the 1 and 2 body integrals. And there are a number of other options here. I'm not going to go into everything in detail. You can look at the API documentation for this diagonalized fermionic Hamiltonian function for more details, but I will call out a few important ones. So max iterations will give the number, the maximum number of configuration recovery iterations you want to run, and num batches is the number of sub samples of configurations that you want to perform in each iteration. And samples per batch, yeah, so the way that SQD works is we sample configurations from the quantum processor, right? But we'll actually subsample batches of smaller batches of configurations, because if we included all of them, we wouldn't be able to perform the diagonalization. And samples per batch specifies the number of bit strings we want to include in the subsample. Now, 300 might seem like a small number, and it is actually small for the purposes of this tutorial, but you should also keep in mind that there's this symmetrized spin argument, which we're setting to true, and What that means is we're going to perform a certain operation that expands the set of bit strings by performing like a kind of Cartesian product operation. So the final dimension of the subspace that you're going to be diagonalizing in is going to be more than the samples per batch. It's actually going to be something like the square of it. So that's just something to keep in mind. And again, you can look at the documentation for more details on this spin symmetrization operation, which you can also turn off if you want. Great. So that's how you actually perform the diagonalization, and it returns the result. So here we're actually printing out some of the information from the diagonalization. So we can see that as we perform more iterations of configuration recovery, the energy is going down. And then finally, we're going to visualize the results, and we can see that as we proceed with more configuration recovery iterations, the energy does go down. In this case, the final result is still quite far from the exact solution. However, we didn't include many configurations because we wanted the tutorial not to take so long to run. But if you want to improve your results from SQD, probably the main arguments to play around with here are the samples per batch. So when you increase the samples per batch, that'll enlarge the subspace in which we're performing the diagonalization, so you'll get a more accurate result. However, keep in mind that the computational resources needed to perform the diagonalization will increase accordingly. And the other key option, I would say, is the max iterations, where we can run more iterations of configuration recovery, because as you can see in this plot, the energy was still going down, right? So if you run more iterations, then the energy will keep going down. And there's also the carryover threshold, which you can play around with, and this is Mario alluded to this when he discussed how we actually, after the original SQD experiment came out, we improved on the algorithm by implementing a procedure to retain important configurations from the previous iteration of configuration and recovery. So you can play around with that argument too. And yeah, so that's all I'll say for now for this tutorial. And again, I encourage you to look at the documentation, specifically of this diagonalized fermionic Hamiltonian function, for more details on SQD. Okay, and now I'm going to hand it back to Mario, who's going to tell you about Hamiltonian simulation for dynamics.
Thank you, Kevin, for your hands-on session on the SQD method. Now we can switch gears from Hamiltonian eigenstates to Hamiltonian dynamics, the simulation of the time-dependent Schrödinger equation. Once again, I'll give you some indication of why this is an interesting problem, especially for quantum computation, starting from research by partners that is in part highlighted at QDC. So there's a common thread in all these calculations, such as this one from Brookhaven National Laboratory. Essentially, you start with a quantum system in equilibrium under some Hamiltonian that is somehow perturbed from this state of equilibrium. The perturbation leads to some non-trivial time evolution of the quantum state, and you're interested in how the system evolves under this perturbation, or relaxes after the perturbation has been applied. Typical situation is that of scattering experiments, in which you have particles that are hit with radiation or with other particles, and you look at the scattering cross-section. Now, in this study from Brookhaven National Laboratory, what is studied is relaxation dynamics after a quench. We have essentially an additional term to the Hamiltonian that is suddenly switched on at some time. And then what is interesting is to observe how observables, measurable quantities like this Néel operator that captures antiferromagnetic correlations evolve in time after the quench. There's typically a relaxation, and then there's a transient, which here was simulated on quantum devices with a product formula, a Trotter approximation. A quench is not the only way in which one can change the state of a system and lead to a non-trivial time dynamics. One is the application of a periodic drive, which is featured here in a study by Bask and Riken. By periodic drive, we mean an external potential that satisfies a periodicity property, it's cyclical. And then the team has been looking at how properties like the spin density on top and the spin-spin correlation functions at the bottom evolve in time as this drive, this periodic drive, like a hammer repeatedly hitting the system, is applied. Of course, there are situations like condensed matter in which you look at an external potential or a driving force and so on, but Hamiltonian evolution is crucially important in many different fields. One of them is high-energy physics, where scattering experiments, for example, are performed very, very frequently and can be computationally characterized in terms of the time evolution of a system. Here's an example of an application in high-energy physics from Bask, where essentially they consider a lattice gauge theory formulated in terms of a Hamiltonian, and then look at the dynamics of certain operators called string operators that give them information about the confinement phenomenon. It's a particular application of the many that exist in high-energy physics, and more of it will be covered in the contribution by Fraxanet and Kobos, and pardon, and in the challenges that will be reviewed by Pedro Rivero. These are recent applications, larger in scale than those that were possible before, certainly very exciting, but also from the theoretical viewpoints, there are reasons to be excited about the possibility of simulating time evolution on quantum computers. Indeed, for a broad class of Hamiltonians, not all Hamiltonians, but many of them, some of which are very physically relevant, sparse Pauli operators, K-local operators, the time evolution for a time t can be simulated with an error, let's say epsilon, at a cost that is polynomial in system size, evolution time, and inverse of the target error, up to polynomial. This statement that essentially one can achieve a controllable error with polynomial resources is more formally understood as the BQP complexity class, bounded error quantum polynomial. The simulation of time evolution is in the BQP complexity class, making it a very compelling problem for quantum computers. Not only that, but also any problem in the BQP class, any problem that a quantum computer can solve at polynomial cost with a controllable error can be reformulated in terms of a Hamiltonian dynamics process, in terms of the simulation of the time evolution under a perhaps a bit more exotic Hamiltonian. This argument is known as BQP completeness of the Hamiltonian simulation problem. These theoretical properties make the simulation of time evolution a very natural application for quantum computers and a candidate in the search for quantum advantage. There are, however, certain caveats which are important to keep in mind and which are the subject of very interesting research and the development of techniques such as those that Kevin will be covering in his second tutorial. In the previous chart, I made no mention whatsoever of noise or imperfect implementation on quantum operations affecting the calculation. The BQP argument holds for a noiseless quantum computer. However, if we are doing a simulation in presence of noise, unwanted components in the dynamics of the device itself, instead of producing the target state, we will produce some other quantum mechanical state, and the stronger the noise, the more different this state, the farther away this state will be from the target state that we want to prepare. And so the kind of accuracy in those theoretical arguments may not be guaranteed in the presence of noise. Naturally, practitioners don't simply accept noise as a fact and do nothing about it. Of course, there's the effort of lowering the error rates at device level, but at the level of algorithms and demonstrations, there is error mitigation. For example, trying to produce a collection of states as it is done in zero noise extrapolation and with varying noise strength and trying to extrapolate towards a noiseless answer. There is also, and that's going to be covered in Kevin's tutorial, very interesting opportunities at the interface between classical and quantum computation for circuit economization. So in other words, if we can approximate the target quantum circuit with another quantum circuit, maybe more shallow with fewer quantum operations, we can obtain, and without accuracy loss, we can obtain comparable properties, maybe though with a much reduced bias because a smaller circuit is less affected to noise. This topic of approximate quantum compilation is a very interesting technique and one that can make life very easy in performing demonstrations, especially on near-term quantum devices. This field, AQC, will be one of the subjects of Kevin's tutorial. The other caveat that is good to keep in our mind is this. For quantum computations without noise, we have this very nice BQP argument, which translates in very practical algorithms like product formulae. On the classical side, it is true that the approaches that we know about to simulate Hamiltonian dynamics don't have an equivalent argument. They all formally either don't converge or have an increasing cost for a generic Hamiltonian simulation task. However, there are many situations in which a classical algorithm can deliver very accurate results. Granted, there is an underlying approximation scheme, and that's extremely important for us, not only because it's important to know the classical algorithms, make use of them, but also to keep observing the relative growth and precisely gauging the growth of the capabilities of quantum computers. A family of classical algorithms that are being used more and more for the simulation and the characterization of quantum circuits are tensor networks, wherein very concisely one is trying to take the combinatorially large wave function that would correspond to a time-evolved state and compress it in a way that reflects a certain entanglement structure in the wave function itself. If this compression operation, which is done through linear algebra operations and truncations, doesn't lead to an accumulation of errors, our tensor network is going to be very accurate. When that's the case, we have a very good baseline, for example, to benchmark the performance of a quantum algorithm. So it's very important in general to keep in mind that classical algorithms can be very powerful. They can teach us a lot about the quantum algorithms, the quantum circuits, and they can also teach us many things that we can transport in our field. And that will be part of the message in Kevin's second part of the tutorial. I'm gonna conclude on a note. The note is that one of the overarching goals of the quantum computing community is to make quantum computers and algorithms useful and indeed advantageous. And a part of it is certainly and crucially the development of quantum hardware, but also algorithmic research plays a major role in economizing and broadening the scope of applications of the quantum simulations. With this, I thank you very much for your attention, and I leave the floor back to Kevin for his second part of the tutorial on approximate quantum compilation using tensor networks. Thank you.
Hey everyone, so now I'm going to give you a brief tutorial on approximate quantum compilation with tensor networks, and this is a tool that we've developed into this Qiskit add-on, which we call AQC Tensor for short. And again, here are some research papers that you can read about the technique, and here's the link to the GitHub. Now, the way that AQC Tensor works, I guess the idea is you can think of yourself as having a circuit that has a number of gates, except maybe it's too long. With noisy quantum processors, the gates have errors, so if we execute too many gates, then we might lose all of the signal in our computation. So what we'll do is we're going to take the initial portion of the circuit, some initial portion, and we will compress it and create an equivalent circuit, or a nearly equivalent circuit, that has fewer gates. So now this smaller circuit here is performing the same job as this larger circuit here, and so at the end of the day we have another circuit that has much fewer gates but performs the same or nearly the same operation as our original circuit. Now, one of the main use cases for this technique is trotterized time evolution, and so this is the example that we're going to go through in the tutorial. And one thing to note is that the way we're going to compress the circuit is by using tensor network simulation. And one of the reasons that trotterized time evolution is a good application is that at the very beginning for small evolution times, the circuit can usually be simulated by tensor networks, which are not going to be applicable in the most general case. Okay, so to get to the tutorial, here I'm still on the IBM Quantum platform. And the AQC Tensor tutorial here is, you'll find it in the Qiskit add-ons section, and here it is. approximate quantum compilation for time evolution circuits. Again, I'm not going to go through it in detail. I'm just going to point out a few key aspects which I hope might be helpful when you go through this tutorial yourself. So here we're just going to set up the Hamiltonian that we're going to use as an example. So here we're going to be using an XXZ model, and in the first part of the tutorial we just do a small model that has 10 sites, and here's the expression for the Hamiltonian, and this is the code to generate it. And we're also going to create an initial state, which is just going to have some X gates applied to the all zero states, so it's creating some computational basis state. And for this workflow, we're going to pick some evolution time that we want to perform. And the first part of that evolution is going to be performed by an optimized AQC circuit. So this is going to be a compressed circuit. And then the remaining time evolution is going to be performed like we would usually do with trotterized time evolution. So we're going to have these two halves of the circuit, and we're going to combine them. And then the combined circuit will perform the full time evolution. And in this example, we're going to choose 0.4 as the total evolution time, and we're going to split it in half. From time 0 to 0.2, we're going to perform the evolution with AQC Tensor, and then from time 0.2 to 0.4, we're going to perform just a normal trotterized time evolution. Now, if we didn't have AQC Tensor, again, we would have to do normal time evolution. So for the subsequent segment, we're going to choose a number of trotter steps, which is 3. However, for the initial segment, because we're going to be using AQC Tensor, we can actually pick a larger number of trotter steps to target. So here we're setting the target number of trotter steps to 32, but remember, we're not actually going to be performing 32 trotter steps. Rather, what we're going to do is we're going to try to approximate time evolution by 32 trotter steps with a circuit that looks like just a single trotter step. So we're going to compress a circuit for 32 trotter steps down to a circuit with only one trotter step. And again, the number 32 here is somewhat arbitrary, right? As long as, in principle, you would want to set this to a number that is high enough to give you an accurate simulation, but also which you'll be able to handle computationally, because the more trotter steps you do, the more difficult the classical simulation is going to become. But again, for time evolution, the tensor network should be able to simulate relatively high numbers of trotter steps. So, okay, so this is the code for constructing the target circuit with 32 trotter steps, and then here's the code for constructing the subsequent circuit, which only has 3 trotter steps. And yeah, we're going to create a few more circuits here. So the comparison circuit's going to just have the initial evolution time at 0 to 0.2, but using only 3 trotter steps. So that's to represent what we would be doing in the normal situation in the absence of AQC. And also the reference circuit here is supposed to be computing the exact time evolution. So we're going to set that to just have a large number of trotter steps, in this example 200, but again, this is kind of arbitrary. It's just a large enough number that the time evolution can be considered essentially exact. And that's just so we know what the exact answer is, so that we can see how well we're doing. So as I mentioned in the beginning, the actual circuit for the initial segment of evolution we're going to perform is going to look like it only has one trotter step. So that's why we're setting the ansatz number of trotter steps to 1 here. And yeah, so in this case, we're performing a time evolution with only 1 trotter step and then converting that into an ansatz. So if we perform time evolution with 1 trotter step, right, we get a concrete circuit with some parameters, and then what AQC tensor does, this function generate ansatz from circuit from AQC tensor is going to take this circuit and it's going to convert it into an ansatz, right? So now we have a parameterized circuit with the structure of a single trotter step, but it's extracted those gate parameters so that we have an initial starting point for the optimization. Now, yeah, so here we're just printing out some of the depth numbers. So the target circuit, which is the one with 32 trotter steps, has depth 385, and but our ansatz only has depth 7, right? So we're going to be trying to compress a circuit that originally would have had depth 385 down to a circuit with depth 7. And for comparison, if we had 3 trotter steps, the depth would be 36. So that would be what you would see in the normal case. And to do the compression, we're going to use tensor network simulation. So here we recommend using QIM, which is a tensor network simulation library for Python that we've integrated with the AQC Tensor add-on. And yeah, so here we're initializing, we're basically converting our circuits to tensor networks. So here we're using MPS, which stands for matrix product state, and we're using MPS as our tensor network structure. It's a one-dimensional tensor network structure, but in principle, you can use different kinds of tensor networks. Here we're just using MPS for simplicity and because it works, but again, at more advanced situations, you can consider different kinds of tensor networks. And so this is showing what the bond dimensions of our tensor networks are. And here we're computing the initial overlap between our tensor network, our tensor network with the tensor network for the exact evolution. And the goal is to adjust the parameters of our tensor network to maximize the fidelity with the target tensor network. And here you can see the starting fidelity is already quite high. That's because this is just a small example. In the second part of this tutorial, there is going to be code to scale up this example, and in that case, the starting fidelity won't be so high. So, and here, this is the code to perform the optimization, and this is showing that we're choosing an objective function to maximize the state fidelity, and the optimization is actually just performed with scipy.optimize.minimize, which is a fairly widely used optimization function in the Python ecosystem. And here we're passing the Jacobian because we're actually using JAX to automatically differentiate the objective function, which helps with performance. And you can see here the progress of the optimization. As we perform the optimization, fidelity increases, and the optimization also returns the final parameters of our circuit. So once we have those final parameters, we can call this function here, assign parameters, to put the parameters back into our circuit. So now we have the finalized circuit for performing the initial segment of the time evolution. So just to review, right, we started with a circuit with only one trotter step, and we took the gate angles in that circuit as the initial parameters for our tensor network optimization. The optimization returned a new set of parameters, and then we plug it back into the single trotter step circuit, so that now that circuit, which only looks like a single trotter step, can reproduce the evolution that you would get with 32 trotter steps. And now we compose that circuit, the single trotter step circuit, with the subsequent circuit to get the final circuit to perform our time evolution from time 0 to 0.4. And yeah, the rest of this is just pretty standard. We're going to be transpiling the circuit down to the instruction set architecture of a specific hardware backend. And when we run it, we can see all of the results. So here you can see that the exact value here is minus 0.5, and with AQC we get a somewhat close answer, whereas if we had done the evolution without AQC, we would have gotten a much different answer due to the noise in the hardware. So yeah, that's all I'll say about this tutorial, and yeah, you can run it for yourself, and hopefully this helps you understand some of the tutorial, and hopefully you'll find that AQC Tensor is useful for your own work. And with that, thanks for listening.